Venus, Earth's evil twin that could teach us about our future. Part 1. Venus as a near twin of Earth. Venus, frequently dubbed Earth's sister planet or evil twin, initially presents a facade of remarkable similarities to our home world, prompting early scientific and speculative interest in its potential habitability. Both planets share a comparable size, with Venus's diameter being only slightly smaller than Earth's, and their masses are also quite close, resulting in similar gravitational pulls. This close resemblance extends to their bulk composition, suggesting that they aggregated from similar proportions of rocky and metallic materials in the protoplanetary disk. Such fundamental similarities led many astronomers and science fiction writers to envision Venus as a verdant world hidden beneath its perpetual cloud cover, perhaps teeming with life or at least offering a more temperate environment than its current reality. This foundational likeness made Venus an attractive target for early space missions, driven by a desire to understand why two planets, born so similarly, could evolve down such dramatically different paths. The gravitational interactions and orbital mechanics that shaped their early solar system environment would have been largely the same, setting the stage for what, on the surface, appeared to be parallel evolutionary trajectories. However, the superficial similarities belie a profound divergence in their actual environments, a cosmic object lesson in planetary evolution. Despite their shared heritage in terms of size and composition, the current states of Venus and Earth are diametrically opposed, making Venus a stark warning rather than a welcoming twin. Earth enjoys liquid water, a breathable atmosphere, and a dynamic biosphere, while Venus is a parched, superheated, and chemically corrosive inferno. This dramatic contrast underscores the intricate interplay of factors that dictate a planet's long-term habitability, including its atmospheric evolution, geological activity, and the presence or absence of a strong magnetic field. The comparative study of these two worlds is therefore invaluable, providing scientists with a natural laboratory to explore the critical thresholds and feedback mechanisms that can either foster life or extinguish it. By dissecting the differences in their histories, from their primordial atmospheres to their current geological processes, we gain crucial insights into the complex recipe for life and the fragility of planetary equilibrium, making Venus an indispensable case study for understanding our own planet's future. Part 2. Runaway greenhouse effect and deadly heat. The defining characteristic of Venus, and the primary reason for its inhospitable nature, is its extraordinarily high surface temperature, which consistently hovers around a blistering 462 degrees Celsius. This extreme heat is not merely a consequence of its closer proximity to the sun, but is overwhelmingly driven by a relentless and pervasive runaway greenhouse effect, the most extreme example known in our solar system. Venus's atmosphere is composed almost entirely of carbon dioxide, accounting for over 96% of its atmospheric gases, making it a super-efficient insulator. This dense blanket of CO2 traps solar energy with devastating efficiency. Sunlight penetrates the thick cloud layers and warms the planet's surface, but the infrared radiation re-emitted by the heated ground cannot escape back into space. Instead, it is absorbed by the CO2 and re-radiated downwards, leading to a continuous and accelerating accumulation of heat. This process has transformed what might have once been a potentially temperate world into a planetary furnace capable of melting lead and rendering it utterly inimical to life as we understand it. The atmospheric pressure at the surface is also crushing, approximately 92 times that of Earth's sea level pressure, further contributing to the extreme conditions. The runaway greenhouse effect on Venus serves as a profound and chilling demonstration of positive feedback loops in climate systems, offering a cautionary tale for planetary science. Scientists hypothesize that early Venus may have possessed significant quantities of liquid water, potentially forming vast oceans. As the young sun grew hotter over billions of years, or perhaps due to other initial warming mechanisms, surface temperatures on Venus began to rise. This led to the evaporation of liquid water, transforming it into water vapor, which itself is a potent greenhouse gas. This additional water vapor further trapped heat, causing more water to evaporate, creating a vicious cycle. Eventually, all surface water boiled away, and the water molecules were gradually broken down by solar ultraviolet radiation in the upper atmosphere, with the lighter hydrogen atoms escaping into space. The remaining oxygen reacted with rocks or was also lost. This irreversible process not only stripped Venus of its vital oceans, but also locked in the extreme superheated state we observe today, permanently altering its habitability. Understanding the precise mechanisms and timescales of this runaway process is crucial for assessing the long-term climate stability of Earth and other potentially habitable exoplanets. Part 3: Volcanoes and Resurfacing Mysteries. Venus is a planet of intense geological activity, with its surface characterized by an astonishing abundance of volcanic features, ranging from expansive lava flows to towering shield volcanoes and unique pancake domes. However, unlike Earth's dynamic crust, which is constantly reshaped by the slow but relentless movement of tectonic plates, Venus appears to operate under a different geological paradigm. Scientists have theorized that Venus undergoes periodic, catastrophic global resurfacing events, where vast quantities of magma erupt from the interior, effectively burying and obliterating older terrain. This process explains why the Venusian surface is remarkably young, with an average age estimated to be between 300 and 600 million years, exhibiting a relatively uniform distribution of impact craters, rather than the varied ages seen on Earth, or the heavily cratered ancient terrains of the Moon and Mars. The precise mechanism driving these dramatic, planet-wide resurfacing events remains one of Venus's most enduring mysteries, challenging conventional models of planetary thermal evolution and mantle convection. Theories include cyclical instabilities in the planet's mantle leading to episodic overturns, or a stagnant lid regime, where the lithosphere is too thick to undergo plate tectonics but occasionally collapses in widespread volcanic outbursts. Thousands of volcanic structures are scattered across the Venusian landscape, providing compelling evidence of a history rich in igneous activity and possibly ongoing volcanism today. Radar mapping missions, particularly NASA's Magellan spacecraft, unveiled a diverse array of volcanic landforms, including enormous shield volcanoes that rival Earth's largest, extensive networks of lava channels stretching for hundreds of kilometers, and unusual dome-shaped structures resembling solidified blobs of viscous lava. These features attest to the immense scale and power of Venusian volcanism. Determining whether these volcanoes are still active is a critical area of research. Recent data from orbital missions hints at transient thermal emissions and atmospheric sulfur dioxide variations that could be indicative of present-day eruptions. Understanding the nature and frequency of Venusian volcanism is paramount for deciphering the planet's internal heat budget, how it has cooled and degassed without the benefit of plate tectonics, and what implications this has for its atmospheric evolution. The distinct geological evolution of Venus offers a unique contrast to Earth, highlighting alternative pathways for planetary internal dynamics and surface rejuvenation. Part 4: Clouds of sulfuric acid. Shrouding the infernal surface of Venus is a thick, perpetual veil of clouds, not of water vapor as on Earth, but predominantly composed of concentrated sulfuric acid droplets. These dense, yellowish-white clouds extend from altitudes of about 45 kilometers up to 70 kilometers, forming multiple distinct layers that effectively obscure the planet's surface from direct optical view. Their highly reflective nature is responsible for Venus's brilliant appearance as seen from Earth, earning it the moniker morning star and evening star. However, this seemingly benign reflectivity plays a complex role in Venus's climate. While it reflects about 75% of incoming sunlight back into space, thereby initially cooling the upper atmosphere, the clouds simultaneously contribute to the planet's greenhouse effect by trapping infrared radiation below them. The formation of these corrosive clouds involves a complex cycle of photochemistry in the upper atmosphere. Sulfur dioxide, SO2, likely sourced from volcanic outgassing, reacts with water vapor, H2O, under the influence of ultraviolet radiation from the sun to produce sulfuric acid, H2SO4 aerosols, which then condense to form the cloud droplets. The sulfuric acid clouds are not static. They are driven by powerful atmospheric circulation patterns, manifesting in dynamic movements and distinct morphological features when viewed with specialized filters. While precipitation in the form of sulfuric acid drizzle does occur from these clouds, the extremely high temperatures in the lower atmosphere cause the acid droplets to evaporate long before they can reach the planet's surface. This constant cycle of condensation, precipitation, and evaporation sustains the pervasive cloud cover, ensuring that the Venusian surface remains hidden. The corrosive nature of these clouds poses formidable challenges for spacecraft exploration, requiring specialized materials and robust shielding to withstand the harsh chemical environment. Any probe descending through this atmospheric layer must contend with not only intense heat and pressure, but also the highly reactive chemical composition. Studying the properties and dynamics of these clouds is vital for understanding the complex chemistry and energy balance of Venus's atmosphere, offering insights into atmospheric processes under extreme conditions that may not be directly analogous to Earth, but are crucial for a comprehensive understanding of planetary atmospheres. Part 5. Strange Winds and Superrotation. One of the most perplexing and fascinating phenomena in the Venusian atmosphere is its remarkable superrotation, a state where the entire global atmosphere circulates around the planet much faster than the solid body itself rotates. While Venus has an incredibly slow retrograde rotation, taking a sluggish 243 Earth days to complete just one turn on its axis, its atmosphere, particularly at the cloud tops, hurtles around the planet in a mere 4 Earth days. This results in incredibly powerful zonal winds, predominantly eastward, reaching speeds of up to 360 kilometers per hour, 224 miles per hour, at the cloud top altitudes of 60 to 70 kilometers. This extreme atmospheric velocity, dramatically outstripping the planet's rotational speed by a factor of over 60, makes Venus's atmospheric dynamics truly unique in our solar system. The exact mechanism driving and sustaining this superrotation is still a subject of intense scientific investigation and debate, but it is believed to involve a complex interplay of thermal tides generated by solar heating, atmospheric waves, and the efficient transfer of angular momentum from the equatorial regions to higher latitudes. The superrotating atmosphere effectively homogenizes and smears out atmospheric features, making it challenging to observe persistent, distinct weather patterns comparable to Earth's familiar storm systems. Instead, images from orbital missions reveal broad, chevron-shaped cloud patterns and large, transient streaks that propagate with the high-speed winds. Scientists utilize observations of cloud movements at different altitudes, particularly in ultraviolet light where atmospheric features are more discernible, to map the complex three-dimensional flow and unravel the underlying forces at play. Understanding superrotation is not merely an academic exercise for Venus. It holds broader implications for atmospheric dynamics on other planets and potentially for exoplanets with similar slow rotation rates and dense atmospheres. It represents a powerful example of how stellar energy inputs, combined with specific atmospheric compositions and planetary rotation, can drive vast global-scale atmospheric circulation cells, transforming a slowly spinning planet into one with incredibly fast and globally coherent atmospheric currents. Unlocking the secrets of Venus's superrotation could provide critical insights into fundamental principles governing planetary atmospheres across the cosmos. Part 6: Ancient Oceans and Lost Habitability. A growing body of scientific evidence strongly suggests that early Venus, perhaps for the first 2 billion years of its existence, might have been a significantly different world, potentially harboring vast quantities of liquid water on its surface, including extensive oceans. This tantalizing possibility is supported by several lines of evidence, most notably the elevated deuterium to hydrogen DH ratio in Venus's current atmosphere. Deuterium is a heavier isotope of hydrogen, and its enrichment implies that the lighter hydrogen, primarily originating from water, preferentially escaped to space over billions of years, leaving behind a relatively greater proportion of the heavier deuterium. If Venus indeed once possessed oceans, it implies a past period of potential habitability, where conditions might have been amenable to the emergence and sustenance of life, akin to early Earth. Such a scenario challenges the long-held view of Venus as an eternally hellish world, and opens up intriguing questions about the conditions under which life could arise elsewhere in the universe. The existence of ancient oceans would have fundamentally shaped Venus's early geology and atmospheric composition, creating a climate far more benign than its present state. However, the inexorable increase in solar luminosity over the eons, coupled with a lack of a planetary magnetic field to protect its atmosphere, initiated a catastrophic transformation. As the sun grew hotter, surface temperatures on Venus gradually rose, leading to the evaporation of its liquid water. This water vapor, a potent greenhouse gas, then accelerated the warming trend, creating a positive feedback loop that ultimately culminated in the runaway greenhouse effect. Once the water was completely vaporized, it was subjected to photodissociation by solar ultraviolet radiation in the upper atmosphere, breaking water molecules into hydrogen and oxygen. The lighter hydrogen atoms, unimpeded by a magnetic field, efficiently escaped into space, permanently stripping Venus of its oceans. The remaining oxygen likely reacted with surface rocks, or was also lost over time. This irreversible loss of its ancient oceans represents a critical turning point in Venus's planetary evolution, sealing its fate as an uninhabitable, desiccated world. The history of water on Venus serves as a profound lesson about the delicate balance required for maintaining planetary habitability and highlights the profound impact of stellar evolution and atmospheric escape mechanisms on a planet's long-term prospects for supporting liquid water and, by extension, life. Part 7: Soviet Landers and Venus Missions. The exploration of Venus has been a monumental undertaking, fraught with immense technical challenges due to its extreme environment, yet yielding groundbreaking scientific discoveries. The pioneering efforts were largely spearheaded by the Soviet Union's ambitious Venera program, which, beginning in the 1960s, achieved an extraordinary series of firsts in planetary exploration. Venera 3 was the first spacecraft to impact another planet's surface in 1966, albeit without transmitting data. Later, Venera missions accomplished the first atmospheric entry into an extraterrestrial planet, Venera 4 in 1967. the first soft landing on another planet, Venera 7 in 1970, and, remarkably, the first images transmitted directly from a planetary surface, Venera 9 and 10 in 1975. These landers were engineering marvels designed to withstand the crushing atmospheric pressure up to 92 bars and searing temperatures, over 450 degrees Celsius, for brief but crucial periods, typically lasting less than an hour. The invaluable direct measurements provided by these probes, including temperature, pressure, atmospheric composition, and surface imagery, unequivocally revealed the infernal conditions prevailing on Venus, forever altering our perception of Earth's once-thought twin. Following the groundbreaking successes of the Venera program, other nations and space agencies have continued to probe Venus with increasingly sophisticated missions. NASA's Magellan mission, launched in 1989 and operating into the early 1990s, used synthetic aperture radar to meticulously map over 98% of Venus's surface, with unprecedented detail, penetrating its thick cloud cover. This mission revolutionized our understanding of Venusian geology, revealing its vast volcanic plains, intricate lava channels, numerous impact craters, and unique tectonic features, providing the most comprehensive topographical data to date. More recently, the European Space Agency's Venus Express, 2006 to 2014, and Japan's Akatsuki, since 2010, have focused on studying Venus's atmosphere and climate dynamics from orbit. These missions have provided long-term observations of the super-rotating atmosphere, cloud chemistry, and atmospheric escape processes, continuing to deepen our understanding of this enigmatic planet. The collective efforts of these diverse missions underscore the enduring scientific importance of Venus, paving the way for future probes that aim to investigate its interior, atmospheric evolution, and potential for past or present habitability, with even greater resilience and scientific payload capabilities. Part 8. Recent Hints of Phosphine Gas. In a scientific announcement that captivated the world in September 2020, a team of astronomers reported the intriguing detection of phosphine gas pH3 in the clouds of Venus. This finding was particularly significant because, on Earth, phosphine is primarily associated with anaerobic biological activity produced by microbes in oxygen-poor environments. While there are some known non-biological pathways for phosphine production, such as lightning or volcanic activity, these mechanisms are generally thought to be insufficient to explain the observed quantities in Venus's atmosphere. The presence of phosphine in the Venusian clouds, therefore, sparked intense scientific debate and reignited the long-standing question of whether life, in some extremophilic form, could exist within the planet's relatively more temperate upper cloud layers, specifically at altitudes where temperatures and pressures are Earth-like, despite the highly acidic sulfuric acid environment. This possibility, however remote, provided a tantalizing hint that life might persist in unexpected niches even on such an extreme world. The initial phosphine detection, made using ground-based telescopes like the James Clerk Maxwell Telescope and the Atacama Large Millimeter/Submillimeter Array, quickly garnered widespread attention and propelled Venus back into the forefront of astrobiological research. However, the discovery also faced rigorous scientific scrutiny and debate. Subsequent analyses, some using the same data and others employing different methodologies or instruments, have offered both corroboration and challenges to the initial findings, leading to ongoing discussions about the robustness of the detection and the interpretation of the spectral signals. Regardless of whether the phosphine detection ultimately proves to be a definitive biosignature or points to previously unknown geological or chemical processes, Its initial announcement has profoundly impacted the scientific community. It has injected renewed vigor into Venus exploration, spurring proposals for new dedicated missions specifically designed to investigate the chemistry of the Venusian atmosphere at various altitudes, searching for definitive biosignatures, and attempting to unravel the mysterious origins of its atmospheric anomalies. The possibility, however small, of microbial life thriving in an environment so profoundly different from Earth challenges our assumptions about habitability and the diversity of life in the universe. Part 9. Venus in Culture, Love, and Myth. Long before the advent of telescopes and space probes, Venus held a uniquely prominent and captivating position in human culture, myth, and early astronomy. As the brightest natural object in the night sky after the moon, its striking radiance made it easily observable and revered by countless civilizations across millennia. The Romans, deeply influenced by Greek mythology, named the planet after their goddess of love, beauty, sex, fertility, and prosperity, Venus, equivalent to the Greek Aphrodite, precisely because of its luminous and beautiful appearance. This powerful association with love, feminine grace, and passion has profoundly permeated Western art, literature, poetry, and astrology, where Venus continues to symbolize affection, harmony, attraction, and aesthetic values. Its characteristic appearance as both a morning star, visible before sunrise, and an evening star, visible after sunset, further added to its mystique and celestial significance, often symbolizing duality or a harbinger of change. Across diverse cultures and ancient civilizations, Venus has been recognized with various names and attributed with distinct mythological roles, often linked to deities or significant celestial events. The ancient Greeks, for a long time, believed the morning star, Phosphorus, and the evening star, Hesperus, were two separate celestial bodies before realizing they were one and the same planet. Mesoamerican civilizations, particularly the Maya, held Venus in exceptionally high regard, meticulously tracking its cycles and incorporating its movements into their complex calendars and astronomical calculations. Its precise observations were used to predict events and influence religious ceremonies, demonstrating a sophisticated understanding of its orbital mechanics. In many cultures, its prominence in the sky made it a celestial guide for navigators, a source of wonder for philosophers contemplating the cosmos, and an object of deep spiritual contemplation. Even in contemporary society, the symbolic power of Venus endures, embodying timeless themes of beauty, desire, and the eternal allure of the cosmos. Its cultural legacy is a testament to humanity's innate curiosity about the heavens and its enduring impact on our collective imagination, bridging the gap between scientific inquiry and ancient human wonder. Part 10. Lessons from Venus for Climate Change. Venus offers humanity a profound, albeit sobering, object lesson regarding the catastrophic potential of unchecked climate change and the delicate fragility of planetary habitability. Its current state, characterized by an extreme runaway greenhouse effect, serves as the most powerful and unequivocal natural experiment in our solar system, demonstrating precisely how a planet's atmosphere can transform from one that might have been amenable to life into an utterly inhospitable inferno. With an atmosphere composed overwhelmingly of carbon dioxide and surface temperatures hot enough to melt lead, Venus stands as a chilling analog for the most dire, worst-case scenarios of anthropogenic global warming. It underscores with stark clarity the critical importance of atmospheric composition and the precarious balance required to maintain a temperate climate suitable for liquid water and, consequently, for life. The sheer scale of Venus's atmospheric heat trapping illustrates that there are definitive tipping points in planetary climates, beyond which feedback loops can become irreversible, leading to devastating and permanent environmental degradation. The meticulous study of Venusian atmospheric dynamics, its long-term climate evolution, and the processes that led to its runaway greenhouse state provides invaluable data for refining and validating our complex climate models here on Earth. By comparing the divergent paths of Earth and Venus, two planets that started with similar characteristics but ended up so dramatically different, scientists can better identify and understand the critical thresholds, positive feedback loops, and external forcings that can destabilize a planetary climate. This comparative planetology allows researchers to test theoretical models of atmospheric physics under extreme conditions that are otherwise inaccessible, enhancing our predictive capabilities for Earth's own future climate. Venus stands as an urgent reminder that planetary habitability is not a guaranteed, static condition, but a dynamic and fragile state that can be irrevocably altered by changes in atmospheric composition. Its ultimate fate serves as a powerful cautionary tale, imploring humanity to take decisive and comprehensive action to manage Earth's climate, mitigate greenhouse gas emissions, and actively strive to preserve the unique capacity of our home planet to support and sustain life for generations to come. The lessons from Venus are not just about another planet. They are fundamentally about understanding and safeguarding our own.